Good morning, everyone. Uh, so today I'm going to discuss about that what are the various processes are involved in computational fluid dynamics and all. So myself, Dr. Ravikumar Patala. So I'm going to start the session now. So, coming to that, before discussing computational fluid dynamics, what is the advantage of this computational fluid dynamics? You know very well. Whenever you want to check the performance of the any system, so you want to design the one new component, like you want to design that combustion engine, or you want to design that new kind of fluid kind of system, or you want to design the turbo machinery kind of design. So you want to check the performance. So there is some possibilities are there, like that performance can be estimated either by you conducting the experimentation, or either by you conducting the theoretical study like analytical approaches and all you can solve. And you can have another option like you have to numerically solve that problem. So whenever you want to conduct an experimentation, it is more realistic, but the problem is that it is like equipments are needed, and uh, you want to you want to test for the bigger systems and all, and we want you first we have to make some prototypes, and after effectively successful this kind of system, and then only you can plan for the bigger system. So whenever you want to conduct that parametric study and all, it is very difficult for that this experimentation approach. So there is another approach is called theoretical approach. So these are all actually so physical formulas. What are the mathematical formulas are involved in that geometry, and whatever the mathematical formulas are involved for solving that physical models and all. So we have to we need to solve that analytically, and we need to write your own code, and you can test that performance. So this is also like it is not a feasible solution. Why? Because this is only restricted for small kind of problems like one dimensional, two dimensional problems we want to solve, mean that is okay. But whenever you want to design for the 3D models and all, so that is very difficult, and solving the problems also not an easy task. So there is another approach called computational domain. So this is complicated. Even the complicated problems also, it's possible to complicated designs also we can able to solve it. So the problem one of what are the disadvantages are we can get that some numerical errors like truncation errors and all, and it takes a lot of computational cost. Sophisticated computations are needed. So and time also it will take a lot of time. So we need to discretize that entire domain. So it takes a lot of elements, a lot of meshes and all. It will take, and each and every mess you have to apply the governing equation. So it takes a lot of time to solve that equation. That is the only disadvantages. Okay. So what is actually the CFD? So among all approaches, so CFD is actually discrete solution of real world fluid flow problems. Like if we have any real world fluid flow problem, so that we have to discretize it. We have to discretize that entire problem. Okay. So that discretization, so this discretization solution is obtained at any finite collection of space points and discrete time of labels. Like you have a domain, you are creating water, which is, let us take some small example. Your water will be flowing in that pipe. So what you can do, you want to study that how the velocity will be varying, how that pressure will be varying in that particular pipe. So what you can do, so we can take that entire geometry, and you have to discretize that each and every geometry. So like until this into small elements. So we have to discretize the solution. Okay. So we have to discretize the solution, and we have to and each and every point you have to apply that equation. So uh, once you each and every each and so you have to apply that set of governing equation. You have to apply the set of boundary conditions you have to apply. So for ultimately at each and every nodal points and each and every discretized spatial points, these equations will be solved. These partial what are the equations will be involved for the flow. So partial differential equation, whatever it may be, that can be solved by using any kind of scheme. So we have different approaches like finite difference method, and finite volume method, finite element method. So these are the most common uh, to solve the discretized problems. And nowadays, some advanced computation techniques like lattice Boltzmann technique also now it is evolved. And now if you want to solve some crack analysis and all, if you want to say peridynamics kind of softwares also, approaches also now it is going. And now, so what are the benefit of this CFD? So better detail in short time. So if you want to model any experimental kind of setup and all, so I cannot build that entire experimental setup. So that you have the CAD, you can take that CAD models. You can import it, and you can do that discretization, and you can give that boundary condition. You can give that problem statements and everything. You can give it. So we can so that your experimentation time will be reduced. So for building a experimentation time will be reduced. That is one of the benefit. And design better and faster and economical and meet environmental regulation and ensure the industry compulations. So this is the thing. Now design a better and faster. Like you want to design the accurate product. So what you can do? You want to you want to optimize the particular product. Let us take that engine you want to take. So engine you want to model means. So every time you cannot do that experimentation. So one if you found that any limitation there, you want to change that prototype, and you want to do the experimentation again. And there is if you any issue were found in there, then again you want to change the design. So it is every day repeated experimentation. It is very very costly task, and it is not feasible one. So it is not recommendable one. So what you can do, you can design, and you can do that experimentation in faster way, so with the minimal approximation error. So that is will be possible. And CFD analysis leads to shorter design cycle, and your product get market faster. So whenever you want to make a product, so you want to design a new component, you want to launch that new product in the market. So what you can do, so you can design the model, and you can do that simulations, and you can get that any optimization for feasibility is there. So based on these approaches and all, and you can decide, you can take that your own decision. And after that, so once the product was filed, so from that product was filed, and then you can do that small prototype, and you can test it in real time atmospheric condition. And if it is fine, then you can launch into the market. So that can be possible. But every time doing the repetition experiment and all, it is not possible. So for that, so you can do any optimization, geometry optimization and all, you can do it in your CAD model. So those models will be incorporated into the CFD, any of the commercialized CFD software, and you can do that real-time experimentation. And once it is product was finalized, so then you can do that real-time experimentation, and you can launch into the market. That can be possible. That is one of the benefit in the CFD. And in addition, equipment improvements are built and installed will be minimal downtime. So no need to installation of any equipment, and no need to build any experimental setup, and so that your experimentation time will be minimized. So, and apart from that, and CFD is a tool for compressing the design and development cycle, allowing for rapid prototyping. So once it is models was done, you already model well done, and you are doing that simulation, and you are optimize that performance. So the same models, so you just directly connected to that any rapid prototype system like 3D printing and all, and you can feasibility to manufacture the component. So that those are the benefits of the CFD. So why CFD? So for doing the analysis and all, like simulation based design instead of build and test. So whenever you want to do that experiments and build and test method, generally we have to do in the olden approaches and all. But that can be eliminated. So we can completely go with that simulation based design instead, build and test approach. So, and CFD provides high fidelity database for diagnosis flow fields. Like if you want to find out, suppose you have a product that you want to attach that any diagnosis in that particular geometry. So what you can do, you can design. You already have the design for model, so that you can import into that CFD, and you can test it, and you can find that any diagnosis. If any geometrical errors are there, design errors are there, that you can be rectified. So that is a thing. And simulation of physical fluid phenomena that are difficult for experimentation. So real-time experimentation conditions, it is very difficult to incorporate there. So you can do we can do the simulation over there. So that is a one of the benefit. And full scale simulation, like complete setup, you can launch and you can do that full scale simulation and all. You can perform it, like you can take the ships and aeroplane, and then how the drag condition, how the drag will be acting, how the lift will be acting. So those kind of analysis and all, we can perform it in a full scale condition also. It is possible to do the analysis. And is there any where environmental effects are there, that and also you can able to check. Like suppose you are launching your one vehicle. So in the vehicle, in the car and all, outside atmospheric condition, let us take some temperature was there, 45 degrees temperature was there. Like inside, how the heat transfer will be takes place and all. So that kind of study you want to perform means like whether any weather condition will be affected. Like when you are moving with the car, so wind will be flowing very rapidly. So because of the wind and all, the drag force will be there, so that will be affect to that performance of the engine. So instead of that, your car will be pushing, car has to move opposed to that wind direction. So a lot of force has to be acting on there, and a lot of shear force will be acting on the your car body. So those kind of effects will be estimated in the CFD. And hazards, like any explosions will be there. Like due to the explosion, some smoke will be coming, and this smoke how will be distributed over there. And those kind of analysis also is possible. And radiation, and outside solar radiation, how it will affect to that interior parts and all. And any kind of pollutions will be there. Like if whenever doing that chemical reaction and all, so chemical reactors, so like any reaction will be happen, like some what kind of pollution will be evolved. And that can be you can pre-estimate that emission analysis. And you can do that physical problems also. Like, and you can also get some complete knowledge and explore of the fluid physics. So these are uh, the need of CFD. And so where actually this CFD will be used. So we have a lot of industries who adopted this CFD approach. And particularly for automobile and aerospace industry. So when we want to design the car body, so that car body actually, so how to design. So if you design your car body like normally, so whenever the wind will be flowing, so if that is not in that particular shape, it will be create lot of drag. So it will be create lot of drag will be created. So because of the drag and all, so it will be extra effort he has to put for moving the car. So what you have to do, you have to design your car body like such a way that you have to avoid the drag forces and all. So so if you reduce the drag force and all, so obviously it will be indirectly affecting that mileage of your product. So let us, for example, if you have a train, normal train and all, so it is the front part and all, it is not, it is flat in nature. So because of that, more drag force will be acting on that train, normal typical trains, Indian trains. Suppose if we take that bullet train and all, now you can see that front portion. So how well it is designed. So because of that design and all, so what will happen? So air will be flowing and drag force will be eliminated. So you can catch that maximum speed. So that will be possible. So these kind of analysis and all, how we can do. So you can design your models, and so once the models was ready, you can do that simulation. So that can be possible. So in particularly for automobile industries, you want to design the bodies and all, car bodies, aeroplane bodies and all, you want to design to avoid the drag forces and all, that can be possible. So that kind of analysis can be performed in the CFD approach. And various other industries like cement process and chemical industries you can do. And product and manufacturing industries also we can do. And turbo machineries, like we want to design the fan, turbines, compressor, blowers. And based on the turbine design, and how the performance will be there, that performance study also we can do in the CFD. And thermal and nuclear power plants, like how much what suppose you are passing the fluid, and how much it will be converted into steam, and how much temperature distribution will be there. And the nuclear power plant industry, how that temperature will be distributed throughout that nuclear core. And these analysis we can do, these analysis we can do in the CFD. and combustion and fire and environmental pollution that we can do. And for HVAC industries like heating, ventilation, air conditioning, so in shopping malls and all, we are having HVAC units. So how well that the cold air will be distributed, how the temperature distribution or takes place over the interior parts and all that kind of analysis also we can do. And weather forecasting, so based on the solar radiation, so the temperature will be raised. So based on the temperature, how the wind blow will be takes place over the particular city. So those kind of analysis also we can do in the CFD. And defense and space application also, like space application, how that design how the design will be there, and how to optimize the design like missiles and all everything. So based on your CFD analysis. And biomedical application, like nowadays actually 3D printed hearts also will be coming. So suppose you want to test that those kind of models and all, so you want to test those kind of organs and all, so you can design, and you can design it in the CAD models. And blood flow will be how it will be takes place and all you can do in the CFD, in internal flow analysis we can do. So these are the what are applications of the some of the CFD approaches. So automobile industries, aerospace industries, waterfalls and ventilation, biomedical application, and these are the some of the common applications of the CFD. So from these counters, from these velocities, from this pressure gradients, you can see, and you can estimate the physical domain significance. You can estimate it. So typically in the CFD we have a three kind of steps are there. One is the pre-processing and simulation and post-processing. So pre-processing is nothing but when I want to test that design product, so we have to create the geometry and meshing will be there. This is the pre-processing step. So first you have to design the model. Either this design can be done commercial CFD softwares, or else you can design of any of the CAD models. That CAD models we can import it into the commercial CFD softwares. So after these geometries was created, so you can do that meshing and all. So you can do that meshing and all. So once you do the meshing, so we can entire geometry will be discretized into small elements. So in these elements only, from these elements only, so you can start the simulation. So in the simulation you have to put that CFD solver settings and numerical simulations and all we can perform it. So at each and every element, so after done that as meshing at each and every element, so you can implement that all kind of equations like uh, if the flow will be takes place, so you can implement the Navier-Stokes equation. If that like temperature distribution will be takes place, then you can put that energy equation. And if it is like any turbulence models will be there, and those kind of models also you can implement in the particular element. So these equations will be, these governing equations will be putting into the element. And at this element, at each and these will be these parts, these equations will be solved by that any analytical approach or any iterative approach and all. We can solve that equation, and we can estimate that uh, our final output, like what are the temperature will be there, what are the pressure will be there. Those outcomes will be getting. So those outcomes will be analyzed in the post processing technique. So finally, that analysis part will be taken care by the post processing approach. So, in the before CFD approach, we have a kind of modeling and simulation approach will be there. Like I already told that analytical approach. So for using this modeling and simulation approach, you want to solve that any physical domain. So you should have some knowledge on that applied mathematics. You have some knowledge on engineering, biology, and physical science problems. And you have a data, that data has to be processed, that kind of knowledge we have. And numerical analysis and programming skills also needed. But whenever you want to go with the CFD approach and all, you should have some knowledge on the fluid mechanics, and you should have some knowledge on computational science, and you should have a knowledge on numerical methods. So that those most of the CFD problems are like numerical problems only. So those problems will be solved with the help of numerical methods. So what are the steps will be involved in the CFD analysis? So for the first step is real wall flow problems, like you have to design the problem and how the flow will be distributed, and those kind of real kind of geometry you have to design. So after that do the meshing, and the step two, mathematical models will be you have to build. So like these mathematical model which will be includes any governing equation. Suppose let us take the conduction. Let us take that conduction will be takes place. Those conduction equation for Fourier's law of conduction equation we have to apply. And if it is like Newton's law of cooling, H delta T, those are the governing equation. Like if it is that flow will be takes place, conservation of mass equation we have to apply, and Navier-Stokes equation we have to apply. If it is the energy equation, energy will be involved, like temperature distribution will be involved. Energy equations also we have to deploy. And after that we need to give that some initial condition and boundary condition. So once that mathematical models were done, given, so these mathematical models will be solved by solved by algebraic equations. And after that we need to apply that any of the boundary conditions. So so based on the your problem statement, so those boundary conditions you have to give that. After that finally you can get that values. So here that and meanwhile, so the what are the governing equation you are giving here? So like Navier-Stokes equation and all, what are the equations you are giving? So those we need to discretize that equation. So we need to discretize the equation by using that any of that approach. Like we already having a lot of approaches methods. Like already know that finite volume method, finite difference method, and finite element method. And recently lattice Boltzmann method also will be there. So using those schemes, we need to discretize that governing equations. So Navier-Stokes equation and the energy equation and all, those can be discretized. And after that, if it is like coupling is needed, we need to do the coupling. So sometimes so some parameters which will be involved, like so let us take one condition, natural convection problem if we take. So here density and temperature will be completely dependent. So if the temperature will be rising, it will be density will be reducing. The temperature will be low, density will be rise. So this kind of coupling, so interlinkage will be there. So those coupling, if any parameters are will be coupled together, so those coupling also we need to do. So after that, so after solving this algebraic equation, so your partial differentiation equations will be completely converted into algebraic equation. So these can be solved iteratively, like Gauss-Seidel method, or any, you can take any approaches. So you can solve this algebraic equation, and finally you will get that result. Those results we can visually see by using the some flow visualization techniques, or else we can do that post processing techniques. Finally you can get that result. So these are the common steps for solving that CFD. So typically, if that your geometry was very simple, like one dimensional or two dimensional problem, and so you can incorporate these mathematical models over this geometry and do that meshing approach and discretization approach. Discretization you can do, and after the discretization, you can deploy that governing equation, mathematical governing equations. So you can do your own way. So you can do your hand, you can do on your hands, and you can do if the problem, if you want to solve the problem iteratively, so you can connect to that program, you can write your own code, programming skills are needed. But when the geometry was very complex design, like very complicated design, 3D geometry was there, and the 2D also some kind of curvature structures will be there. So your geometry was very somewhat little bit complicated. So what you can do, so have to do, you have in market. So you have some graphical user interference kind of commercial CFD solvers are available. So using those softwares, you can solve that fluid flow problem. So like most common and most popular used software is ANSYS Fluent. You know very well. ANSYS Fluent is a most commonly used software for CFDs. And your problem, suppose you want to solve the problems related to IC engines, combustion engine and all. So that is also possible in the ANSYS Fluent, but it is not fully adaptive. So what you can do, you can choose the convert software. It is convert software is mainly for solving that IC engine modeling. And sometimes like you have star cma plus software is also available. It is also kind of software. And here basically meant for that automobile industries also we can use. And Comsol is a very popular, most popular safety solver for electromagnetic simulations, like suppose in motors and DC generators, and we have some kind of electromagnetic flux will be generated. This kind of analysis also you can solve in any of the software. But for COMSOL is also, it is most adaptive method for solving those kind of problems. And almost like all commercial software is the same procedure only, but approach is different. Sometimes like for ANSYS Fluent and all, they used to take like a finite volume method, and COMSOL and all they used to follow with the finite element method. And star CMM plus and finite difference method they used to follow. Like it's almost like all approaches are same only. We can go with the pre-processing, and we can go with that simulation, and after that we can do that post-processing. All commercial softwares are following the same procedure, but only thing is that the solvation step, the method they are adopting, the method they are adopting is a little bit different. And graphical user interference also they change from one software to another software. So popular softwares for CFD analysis. So whenever you want to choose that CFD models, there is some your software should be compatible for doing the turbulence models, and it has to be solved for the heat transfer models, and has to solve that multi-phase flow kind of problems. And it is also some reactive flows and all. It will take those kind of problems also. It has to be worked. Oh, and it should be before the software should be adaptable for high performance computing, no, high performance computing. And also like customization of CFD solvers. Like sometimes your graphical user interface software, it is meant for only fixed boundary conditions. Sometimes my boundary condition was varied. Suppose let us take suppose inlet velocity is fixed. Normally we can take some fixed constant velocity, but in practical real-time application, the boundary conditions will be vary. So velocity will be varied in nature. Like for certain instant of period of time, so velocity will be suddenly raised. After that, suddenly dropped, and after that, suddenly raised. So these kind of varied velocities and all, if you want to define, so that cannot be possible. That cannot be possible for graphical user interference. So what you can do, that graphical user interference will be adapt for this kind of customized boundary condition. It has to adapt this customized boundary condition. So your software should be adaptable for giving your own code also. If you want to give some your own code, that is also, it has to be adapted, so that can be possible. And overall cost is also like each and every software, commercial CFP software, we have some license fee. You have to check that cost also. That is also important. So after that, once the solvation done, you want to see visually. So how the flow will be takes place and all, and how the counters will be developed. So that and all, pre-processing also it should be adaptable. So some softwares and all, it is not give that post-processing, and they'll give up to solving after once you got the result. So there is a separate packages will be available for processing software. So we have to depend on those processing software. So your what are the software you want to select for CFD? It has to compatible for the post processing techniques also. And finally, it should be you can do it has to be adaptable for the parametric analysis also, and result analysis and validation and all. It has to be adaptable. So most commercial CFD solvers for licensing fee. Before doing the CFD, so geometry and all, either you have some packages are available in the CFD software, or else if it is complex designs are there. So what you can do, so you can go with that your own CAD models. Like you can go with that, you can design with that Pro software, or you can design with using SolidWorks softwares. like you have a AutoCAD software, so you can design your own geometry, and those geometry we can save in the .igs format. So after these files, we can after geometry was created, then you can pass into that meshing. We can do that, discretize the problem. So for discretizing also, sometimes your geometry was very big. So your geometry was very big. At the time, your commercial CFD softwares and all, it takes a lot of time, and you want, and your results also depends on how accurately you are doing the messaging. So that is also very important. So message, sometimes most of that CFD problems results will be mainly depend on the messaging. Messaging is nothing but discretization. So for sometimes your commercial software, so like say, ANSYS Fluent, it is not adaptive. Suppose your geometry was very bigger, so we need to precisely you need to precisely do the discretization. It takes a lot of time. It takes a lot of time, and computationally also it is very costly. And suppose your geometry was too small, like micro level micro channels, and all you want to design. So those discretization problems also very difficult. So very difficult. So what you can do? So for you can have a separate kind of meshing tools are available in the market, like ANSYS, ICM, CFD, and T-Grid, HyperMesh, GridGen, and Grid Pro, and Solomi. And these kind of meshing tools will be available in the market. These are mainly meant for the meshing. So once the meshing was done, so you can have these mesh models. You can have a commercial CFD solvers, and you have a open source software solvers also. You can solve it. And commercial CFD solvers means we have a license fee. So we have a most popular CFD solvers are Fluent and ComSol, Star CMM, and CD Adapco, and Numica and Canva. These are the some having the license fee. So otherwise, if you don't have money, so you can go with that open source software also. Like nowadays, very popular also CFD solver is OpenForm, and Code, Staten, and Refresco, and these are the open source solvers. So you can do that meshing in any of the software, any of this available software. Those meshed models will be directly imported into the open source softwares, and we can do that analysis with free of cost. And after solving was done, and you got that result. So those results you can see in the post processing techniques. You can see in the post processing technique. So that can be you can see in the either any of this in commercial CFD solver, these post processing softwares are available. And if it is some, if you go with that open form and all, so what you can do, so you can connect with that any of the CFD post and tech plot, and field view, para view, and sigma plot. We can see that those results and all we can analyze using these kind of softwares. And what are the limitations? What are the limitations? So what are the key limitations of CFD? So main thing is that grid resolution. So uh, whenever you are conducting that CFD analysis, so first thing is that we need to conduct the grid independent study. So that means suppose you are discretizing one problem with meshing. So after doing the meshing, so your problem was discretized into some elements. So like 1,000 elements you are getting. So at that conditions, you are doing that solving. So you are doing the solving, so you got some value. So whenever you are increasing the mass number. So I just go with that 1 lakh. So more precisely I want to study. So those and all, the accuracy will be different. So lower mass condition, the accuracy will be lower only, but higher mass and all, higher massing condition and all, my accuracy will be increasing. So you have to conduct the grid independence test. Meanwhile, if you perform with that higher mass condition, so like a lot of elements you are considering, and a lot of equations will be generating. So computation cost is also more. So it takes a lot of time to solve the solution. So it takes a lot of time. So you have to analyze. So up to what element, so you can get that comfortable accuracy. So that kind of study you can do
grid element study. So this is the one of the major drawbacks. So every time whenever conducting the CFD analysis, we need to conduct the grid independent study, and it will be generate a lot of numerical errors. So like truncation errors and all, it will be coming. So that and all we'll discuss later. So a lot of numerical errors will be coming, and turbulence models, we have a different turbulence model. So suppose the flow will be takes place in the turbulence model, turbulent, if it is laminar flow, laminar kind of equation we can solve. And if it is turbulent means, and based on the turbulence intensity, so and boundary based on the boundary conditions. So we have to deploy different turbulent models. Like we have a lot of turbulent models like K epsilon model, K omega models, and SST K omega model. Like we have different turbulent models will be there. So every time choosing this the turbulence model is a TD task, TDS task. So that is one of the major limitation of the safety. And physical models or modeling also, like physical modeling, geometry condition we have to change. That is also one of the main limitation. And boundary conditions also, like we have a different kind of boundary conditions. And each time based on your physical domain, physical problem, and you have to change the boundary condition. So giving the real time boundary condition is a challenging task in the CFD. And validation and verification. And once that doing the analysis and you got the results, so every time we need to do the validation whether my CFD model was accurately predicting or not. That we need to do testing by conducting that experimentation or validation. And the sophisticated computational resources are needed. Like so it will be depends on the your processor. So how high end processor you are using. So if it is high end processor, it is there, obviously your computation time will be reducing. If it is low end processor you are using, obviously computation time will be takes a lot more. And expertise is needed. So the person who are using the you are using the CFD approach, the person should have the complete knowledge about on physical models, so mathematical knowledge and computational knowledge also is needed. So most of the CFD engineers requires all this kind of knowledge. So these are the limitations of performing the CFD analysis. So what are the mathematical? First thing is that mathematical modeling. Anyhow, step by step we are discussing. The first thing is that in the modeling, it requires like mathematical modeling. It requires geometry and domain, and it requires coordinates and governing equation, flow condition, and initial and boundary condition, and selection of models for different applications. So first thing is that in the modeling, actually it's mainly first whenever you are designing the geometry CAD models are you are designing. So these models will be when you are incorporating. So you have to select the proper coordinate system also. Like we have a that Cartesian coordinate system, we have a cylindrical coordinate system, and we have a spherical coordinate system also. It will be available. And these proper selection of these coordinate system also important for doing that CFD analysis. So once the geometry was ready, and then you have to give that boundary. Sorry, you have to give that governing equation. So what are the possible governing equations? So that we have to analyze it. Suppose in that mostly whenever the flow was takes place, it has to follow the Navier-Stokes equation. This is the Navier-Stokes equation, a three-dimensional Cartesian coordinate system. And this term we used to call this as local acceleration, and this term we used to call it as a convection problem. And this term we used to call it as a pressure gradient, piezometric pressure gradient, and this term we used to call it as a viscous terms. So from that you can see this equation, we know that the continuity equation. And equation of state, this is pressure. If you want to measure the static pressure, so we can use this equilibrium equation. And if it is mass law will be takes place, so you can deploy that equation like conservation of mass equation. That is also we need to solve it. And this is the conservation of momentum, like in the Navier-Stokes equation. This is the term we used to call it as a conservation of momentum. It is which will be involved with the density, and density will be density and velocity, and time, and pressure gradient term will be there, and how that stress will be developed. So because of the flow, so in between the layers of stress will be developed, so that say stress we can you want to calculate that using this term we can define it. And if any external body force from outside any force will be existing, so those kind of force also we can give it and we can solve that equation. So suppose your problem will consisting of the temperature. Like so, suppose let us take some water. So water you are taking in the boiler. So in the boiler, and you are giving the heat. So you are giving the heat, and because of it absorbing the heat, it will be converted into the temperature will be raised. So because of the rising of the temperature, the density difference will be created, and the flow has been occurred. So here the flow will be takes place, and meanwhile it is depend on the temperature. So temperature variant it will be takes place. So here that energy equation we need to deploy. So we need to how internal energy will be changed, and how the temperature distribution will be takes place. So those kind of equation you want to deploy, so you can solve these equations. So this is the conservation of energy equation. This is also we need to deploy when you are doing the CFD analysis. So some of the important points we need to consider while solving the CFD. It is important to note that these equations are often coupled, meaning that velocity, pressure, and temperature fields are interdependent. So already told that. So whenever when solving the CFD, so like there is some kind of some kind of parameters are interlinked. So they are kind of coupled equations will be developed. So because of the pressure difference, the velocity will be changed. So suppose because of the velocity difference, pressure will be varied. Like suppose for example, if you take the nozzle, so let us take the nozzle. So in the nozzle, actually convergence will be there. So when the flow will be takes place, so area will be reducing. So because of the area reduction, velocity will be rising. So once the velocity will be rising, so what will happen? The pressure will be reducing. So here velocity and pressure, those are both are interlinked. So here the pressure is increasing, velocity will be reducing, and the velocity will be increasing, pressure will be reducing. So these are interlinked, and sometimes like those some kind of parameters are involved. Let us take some natural convection problem. So temperature is increasing, and density will be varying. So because of the density difference, velocity will be changing. So here the temperature and velocity will be linked together. So you have to find out that what the parameters are coupled. So what are the parameters are coupled? Those coupled parameters we need to define properly in the CFD. And to solve them numerically, additional techniques such as like uh, some discretized method we need to follow, and we have to solve that turbulent models also. What is that discretized method? Most commonly used discretized techniques are finite difference method, and finite volume method, and finite element method. So using these approaches, we need to solve that problems numerically. Let us take small example. So this is the lead driven gravity flow. So lead driven gravity flow, it is nothing but it is completely liquid was completely filled with that square cavity. So here the flow was takes place. So because of the flow, so here velocity variation will be there. So here the flow will be takes place. So how you want to estimate? Uh, how you want to estimate this velocity variation? So you want to solve it numerically. First, what are the possible equation we need to adapt? So first thing is that here continuity equation is there. So the mass flow will be takes place. So obviously we need to solve this equation, and we have to deploy the Navier-Stokes equation. Among this Navier-Stokes equation, we need to identify the coordinates. So here, this is the Cartesian coordinate system. So we can take that only x and y direction, and also it is only two-dimensional model. So jet relevant terms will be there, that will be eliminated, and having only x component and y component in the Navier-Stokes equation. So this part will be eliminated, and and there is no temperature and also no need to solve that energy equation. We have to solve only conservation of mass and we need to solve the Navier-Stokes equation. So with the help of this equation, uh, these equation only will be deployed for the this existing physical problem, like driven gravity field. And let us take like a flow through a pipe. Suppose if you some kind of water will be flowing over the pipe, and what are the possible governing equation will be there. So here is the coordinate systems are changed. So earlier actually Cartesian coordinate system, so x and y terms will be there. Now it is actually Cartesian polar coordinate system we have to take. So how radial it is varying and angularly it is varying. So r and theta, these are the Cartesian coordinate system. Sorry, polar coordinate system. So we have to use this polar coordinate system, and you can solve the conservation of mass, and you can solve that momentum Navier-Stokes equation in r component, theta component, z component. So you need to solve this equation. Okay, and there is no simply water will be flowing, and there is no temperature rising. There is no variation in heat flux. So we have to solve only these two models: so, conservation of mass equation and the conservation of momentum equation. And let us take another example: natural convection in an enclosure. Natural in an enclosure. Let us take this is the completely locked one enclosure. So and the top and bottom actually the adiabatic condition. So there is no heat transfer exchange between the outside. So but only heat transfer will be exchanged. So here the hot plate will be there. Here the cold plate will be there. So because of the temperature difference, so natural convection will be takes place. So here, what are the possible equations we can take? So here the conservation of mass equation we can take, and the conservation of momentum equation too. And apart from that, energy equation we need to solve. So why we comes to the picture here that because of the temperature involvement, so the flow will be wicked. So because of that condition, we need to solve the energy equations also. So we need to couple that momentum equation and energy equation also. So these are the possible equations we need to solve. And let us take another example: fluid domain and around aerofol structure. So this is the aerofol structure. So this is the external flow. So what are the possible equations will be comes to the picture. So these are the conservation of mass equation will become, and the Navier-Stokes equation we need to solve. And so these equation only it will be you can able to solve. So this is also like only two-dimensional problem. So that's why only x direction and y direction the velocity will be there. So x direction velocity, y direction velocity you can able to consider. And there is no temperature variation. Obviously we cannot solve that energy equation. So we can stick on only these two equations. And after that we need to define the flow conditions. So once giving that boundary, giving the governing equation, we need to give the flow condition. What kind of flow it is? Whether it is a viscous flow or inviscid flow, or it is a external flow or internal flow. Let us take this is the external flow to flow over the this airflow structure. It will be taken. So we have a external flow condition. So let us take the water will be flowing over the pipe. So this is the internal kind of flow. So what kind of flow will be there? So we need to we need to define it. And turbulent or whether it is a turbulent or laminar, we need to define. So if it is a very low velocity condition, obviously laminar flow will be there. If it is a turbulent flow, we need to define the turbulent conditions. So like if it is a turbulent, we need to apply the turbulent equations. We need to apply. And whether it is incompressible flow or compressible flow, with respect to time your fluid properties will be changing. So that is actually compressible flow. It is not changing means it is an incompressible flow. That is also the flow condition also we need to define. And if it is a single phase or multiple phase, that we need to define. Like it is a single phase, suppose throughout that there is no phase change will be occur. So if it is at the boiling condition and condensation section, if it is a phase change will be happening. So it will be forming from liquid to solid. Sorry, uh, liquid to gases phase and gases to liquid phase. So those kind of flow condition also we need to define properly. And if it is like what are the kind of effects will be there, like whether any thermal effect is there, any density effect is there, we need to define it properly. Like if it is density driven means natural convection we need to
natural convection kind of equation we need to adopt, and those equations we need to solve. And if it is like kind of what kind of flow, surface flow it is, if it is a freely moving, like for free surface flow will be there, or else if it is surface tension kind of flow. For example, if it is a flow over the plate, it is a free surface flow. If it is the water will be flowing over the pore structure, so in the pore structure and all, the flow will be takes place in the due to the sun surface tension. So we have to define if it is the surface tension involvement with the surface tension equation also we need to adopt it, and those kind of equations also we need to solve. And if it is a kind of reaction, any reaction will be happening. Suppose let us take combustion. In the combustion, actually petrol actually combust in the oxygen, and some byproducts will be there. So there actually the combustion will be takes place, and some flow will be takes place. And apart from that flow, and we have a different kind of reactants will be coming up. And during that chemical reactions also, so some flow will two, suppose two drugs are near you are going to mix them together, and new composition was prepared, and here the flow also involved. And after that because of the mixing, and some new reactant will be forming. So there we need to give that some special kind of reaction equations we need to deploy. So those equations also we need to solve. So those conditions also we need to give properly. And after that we need to give that initial conditions, or we need to give that initial condition. In the initial condition, like whether it is like kind of a steady flow analysis or unsteady flow, whatever it may be, you need to give some proper initial condition, like initially how much velocity will be there, some approximate values we need to give. So before solving the problem in iteratively, some approximation values we need to give, so that we can these initial condition are actually not affect to that final outcomes, but it will be affect that convergence, how quickly it is converging. Okay, so what is mean by the convergence? So convergence actually you are giving certain goal. So suppose I want to solve the solution until unless some least value. So like that least value it may be 10 to the power of minus 6 value or something, 10 to the power of minus 3. Until unless this iteratively your problem was iteratively solved. So if you give properly, give that initial conditions, so obviously your convergence will be done very quickly, and it not take a lot of time. So these are the one of the parameter which will influence in the CFD. So what you can do? So you can give the boundary a governing equation. After a governing equation, we can give the flow condition. After that, we can give the initial conditions. And after that, we need to give the boundary conditions. So boundary conditions are actually very important. So we have a different kind of boundary conditions, like Dirichlet boundary condition is also known as fixed value type. So let us take for example, if, some flow was taken in the pipe. In the pipe initially the velocity was fixed only. So your velocity value is 3 meter per second, your velocity value 10 meter per second. So that is actually the boundary condition was fixed. So those kind of boundary condition we call it as a Dirichlet boundary condition. And Newman boundary condition, suppose your boundary condition was some kind of gradient or some kind of flux. Suppose mass flux per area, mass will be distributed per area, and heat flux, watt per meter square, like how much of heat we are distributing per unit area. And gradient, temperature gradient, temperature will be vary with respect to time, dot T by dot T. So this, if it is involved with kind of flux, and it is involved with some kind of gradient, so those kind of boundary condition we can give it as a, we can call it as a Newman boundary condition. If it is a constant mean Dirichlet boundary condition. If it is a way, if it is a flux condition like gradient condition, we can call it as a Newman boundary condition. So uh, these are the common things. And what are the common types of flow boundary conditions used in safeties? And suppose let us take this is the pipe flow. And the pipe flow we can give prescribed velocity we can give, and velocity you can give in inlet velocity we can give, and we can give prescribed mass flow rate also we can give, and prescribed pressure we can give, and prescribed total pressure we can give. Total pressure means actually static pressure plus dynamic pressure, and it will be vary. So like those kind of thing we cannot give that pressure value, so we have to give the total pressure. And prescribed temperature we can give. So these are the possible inlet boundary conditions. What are the possible outlet boundary conditions? Outlet finally, outlet actually pressure outlet sometimes we can give. So suppose outlet pressure it is nominal, it is zero sometimes, and suppose if you give it having some backward pressure will be there, so we need to give that pressure outlet condition also we need to give. And mass flow outlet also sometimes the back and some flow was takes place, so mass flow also outlet condition also we can take. So back flow also we can do and outflow also we can do. These are the possible outlet boundary conditions. These are the possible inlet boundary conditions. And sometimes walls also boundary condition we need to define, like there is no slip conditions, like it is simply moving, so there is no gradient which will be existing on that wall to fluid domain. So that is the one of the wall boundary condition. And wall shear stress, this is sometimes whenever you want to solve like aerofoil structure and all. So whenever the flow will be takes place, some drag will be takes place, so there actually some stress will be developed. So those kind of problems, so we need to define that wall stress also, that is also sometimes we need to give the bond as a boundary condition. And sometimes wall temperature, when the flow will be coupled, when the flow will be coupled, so uh, so from solid domain to fluid domain, there is some boundary will be there. So that boundary existing some kind of temperature. So that wall boundary temperature also sometimes we need to give. And sometimes we can give adiabatic conditions also. There is no heat exchange between the outside condition to inside condition. So that kind of adiabatic conditions also we can define it as a wall boundary condition. These are the possible wall boundary condition. These are the possible outlet boundary conditions. These are the inlet boundary conditions. So this is very clear, right? And symmetry boundary conditions also. Sometimes what you can do that axisymmetric kind of problem. So in that axisymmetric problem, so you cannot define that complete geometry. You can make it into off. You can make it into off. So you can solve the solution in the off, and similarly, same kind of results will be exported into the remaining off also. So in those kind of problems, so we have to define the symmetric plane and symmetric axis also. So these are the some of the symmetry possible boundary conditions. So these are the symmetry planes. So let us take, this is the complete domain you are creating. So I don't want to solve the entire domain. So what I can do, so I can take, this is the symmetry part. In the symmetry part only I can solve, and these equations will be applicable to the remaining area. So here that this is the symmetry plane, and this is the symmetry plane we can consider. Okay. And suppose if you take the cylindrical component, so what I can do, so I can make it as R. So here in the this cross section will be split it into two portions, and the middle one will be considered as a symmetry plane. And here the middle line which will be following, that will be we can consider as a symmetry axis. And there is some kind of another boundary condition will be there, that is a periodic boundary condition. So with respect to time your boundary conditions will be changed. Suppose with respect to time your velocity will be changed. With respect to time your pressure will be varying. So those and all periodic boundary condition we can call it as. And something like far field boundary conditions, like far field boundary condition is typically a simulation where the compilation domain is limited and flow field affected by the external condition, like atmospheric conditions which will be affecting. So that is also we can consider as a far field boundary conditions. So how to select based on your physical problem. So we need to select that model. Suppose if it is a viscous or inviscous condition, we have to adapt that Reynolds the problems. We need to adapt the turbulent models and all. We need to adapt. And if it is a compressible or incompressible set of the equation, state of equation, we need to take it. And if it is that single phase, and if it is single phase, it's not a problem. And if it is a multi-phase problem, and we have various multi-phase models will be there, which will be existing. Those kind of models we need to deploy. And if it is energy equation, it is, which will be involved with the temperature. So this energy conversation of energy equation, we need to, those models we need to adapt. And free surface flow, and if it is a bubbly surface tension flow, these kind of models we need to take. And if it is a chemical reaction combustion, we have a set of chemical reaction models will be there. Those we need to select those equations. And after that, so we are taking the equation, and we need to solve. So all the equations will be partial differential equation and direct derivative equation. So these how is all this partial differential equation into algebraic equations. So that this is some kind of schemes will be available. Discretization schemes will be available. So most popular thing is the finite difference method. In the finite difference method, again we have a different schemes are available: central difference scheme, backward difference scheme, and forward difference scheme. So what is the advantage of finite difference method? So this method is very simple. As suppose if you take that finite volume method, your entire domain will be discrete into small volumes, small volume, and through entire counter will be considered as a one element. So every time this finite volume method, if you solve with the help of finite volume method, and the equations are a little bit complex. So if you take the finite difference method, so it will be easily converted into algebraic equation, and it is easily to solve, and can easily obtain higher order approximations. Like we have to take some kind of assumptions, some approximation we have to consider. So those you can get that higher order approximation also, that it will be possible, and gives higher order accuracy of the spatial discretization. That is also one of the advantages. Coming to the disadvantages, if not given special physical principle of the conversation is not automatically enforced to the finite difference method. This is the one of the disadvantages. We should take the special care. You should be take the special care. Otherwise, you can get the lot of numerical errors. So like truncation errors and all, it will be come out. And this method can be implemented only on simple geometry, since the method cannot be implemented with convenience to the unstructured use. So this finite difference method is mainly meant for the structured grid. If it is any unstructured grid was there, it is not suitable. So that is the one of the disadvantage. The finite difference method requires structured grid solve. Okay, and what are the important things we need to consider in the finite difference method? The differential equation, difference equation is called the finite difference method, and finite difference method can easily obtain higher order approximation, and it is required only structured grid. So how this finite difference will be approximated? What are the approximations will be considered? So we have a three schemes will be available. One is the forward difference method, and backward difference method, and center difference method. And the forward difference method, like uh, from one node to another node. So what is the property difference will be there? Like let us take that velocity. So how difference will be there? So based on that forward difference one, so we can solve that equation. Coming to the backward difference means it will take the older results. It will take the older approximation, and it will solve that accordingly backward difference scheme using this formulation. And center difference method, and from that any two nodes, so that between the two centers, that property will be considered, and equations will be resolved in using the central difference method. So after that, you're going to solve this. We have to expand this Taylor series expansion, and we can get that for possible approximation, and we can get if it is a higher order derivative, so we can solve with the help of different numerical approaches. We can solve with the help of different numerical approaches, and these are These are the possible higher order methods, and these are the possible schemes are available. Okay. So the main thing I want to tell is whenever you want to solve in the CFD, the first thing is that either you can go with that either graphical user interface commercial software, or else you can develop your own code. How if you want to develop your own code, what is the steps will be involved. So first thing is that first thing is that we need to design the geometry, and that after that we need to discretize the problem. So the discretize the problem is nothing but you need to convert into small meshes. So you can take the small finite volumes you can take, and each and every mass. So based on your problem statement, see your problem statement, we have to apply the equation. Suppose if it is like only flow will be takes place, you can apply that governing equations such as conservation of mass and Navier-Stokes equations. And if it is like involved with any kind of temperature equations, you can apply that energy equations such as